Hi, it's time for another math easy solution. To discuss further into calculus with parametric curves, and now look at further into surface area and go over part 2 of the proof video. And first I'll recap part 1, so make sure to watch out. I'll put the link in the description below. So basically, recall from part 1 that for a parametric curve that can be written in the form of y equals f of x, the surface area of the surface formed by rotating the function about the x-axis is given by the formula. This one over here, s equals to integral from alpha to beta of 2 pi y times square root dx over dt squared plus dy over dt squared dt. And for these conditions where the parametric equations are written as x equals f of t, y equals g of t, and where t is between alpha and beta, and f prime and g prime are continuous. In other words, their derivatives exist at all times, and g of t is greater than or equal to 0. In other words, y here, which is g of t, is just greater than 0 so that it's above the x-axis, and we can rotate it about the x-axis so we get an actual surface area. And again, where these parametric equations can be written as y equals to f of x, so we can write them as a typical function like this over here. And here's just a visualization of what I mean by surface area. So we take this function y equals f of x from here to here in parametric form. T is equal to alpha at this point here, and t is equal to beta at this point, and then at this corresponds to x equals to b here, x equals to a here, where this is just, again, x is just a function of t, and this is when t is alpha, this is when t is beta across there. And then when we rotate this about the x-axis, we get a shape that looks like this, a 3D shape, and then the area on the outer surface is s. That's our s, and that's the formula there. And in part 1 I went over, so when we have this y equals f of x type of function, but in fact this formula, just like the arc length proof that I went over, is still valid even if the parametric curve can't be written as y equals f of x, i.e. a one-to-one function. So this is a one-to-one function. You could just write it like this. In other words, if for every one x value we have, well, one y value. This is just one y value across there. But what if we don't? What if we can't have that? Well, this formula is still valid. And to do that, we'll use polygonal approximation, exactly the same as with arc length, and my earlier videos on surface area as well for regular functions, improving that. So let's break up the intervals. The way to do this, let's break up the interval from alpha to beta into n subintervals of equal distance delta t, and then use polygonal approximation to first approximate the arc length, and then just sum it around, or rotate that segment around, and I'll get to that in a bit. So this corresponds to the endpoints t0 to t1, t2, etc., all the way in the random one in between ti minus 1 and ti, all the way to tn, where the distance across is exactly delta t, like that. And the corresponding coordinates on the xy plane, I just fixed that typo there, plane is spelled like that, are p0, and then this is the x0, y0 coordinates, p1, x1, y1, etc., all the way to pn, where the coordinates are xn, yn. Then the next step is we find the surface area of the surface formed by rotating one segment about the x-axis, and we'll look at this segment from ti minus 1 to ti. We can then sum these segments up and then take the limit as the number of segments n approaches infinity to obtain the surface area, just as I've done in my earlier videos, and we'll get a Riemann sum, or something that appears like a Riemann sum. So now let's start to just graph what this all means. And what we have is, let's say we had an x y axis. I'll draw this more over here like that. I'll draw this even wider just because it's gonna take a lot of space. So this is the x, this is the y, and now let's draw a curve that can't be written as a y equals f of x formula, so it's not a one-to-one, just to show you how it looks like. So let's say we had something that looks like this, etc. Actually, even more blatant, say it looks something like this. Actually, I just fixed that drawing. So let's say we have something like this. So at this point here, this is at our P0, and then all the way at the final end is Pn, and then we have, again, this is our P1, etc., and then we have random points across it. Across it here, and then let's say we have at this point I'll call this pi minus 1 all the way to here, which is pi. And then so on, we have random points here, here, etc. Now that the x and y distances don't need to be the same, because the only thing that matters is our delta t's are the same. But when you have a random t variable, it doesn't necessarily mean that the delta x, these distances across, don't have to be the same as this. And these could be the same distance as long as the t values, the difference in t from here to here, are the same as from here to here. And now what we have again is at this point here we have, well, t, this is t0, this is alpha, this is the beginning of our interval, and then at here we have t is, this is t, yeah, tn, this is tn, this equals to beta. And now the next step is to use our polygonal approximation. Just draw, basically all it is just draw straight line segments from each point, like this, and something like that, and here, etc., like that and this. So now that we have these segments, and now what we'll do the next step is, well, let's look at this, focus on this one segment pi minus 1 to pi, and then at this point here, this corresponds to, well, xi. And then this point all the way across down here, this corresponds to, well, xi minus 1. And likewise on this side all the way across here, this corresponds to yi. And then this one all the way across here, this is yi minus 1. So now what we have is, again, is a right angle triangle like that. Yeah, we have a triangle where this distance across is delta yi, and then here we have delta xi. And then the hypotenuse is just the distance across, and we'll write this as absolute value of pi minus 1 to pi. This is a way of writing distance. Yeah, now this right angle triangle, well, what that means is we can write this in terms of the delta yi and delta xi, this distance, because of the Pythagorean Theorem. And now the next step we're going to do is we're going to rotate this around the x-axis, or just this one line segment. So what we'll end up having is something that looks like, if this point's there, reflected across, let's say it's somewhere around here, this point would be somewhere across there, like that. And then if we rotate this around, we get a shape that looks like this. And then rotate this around. I'll draw this even better. I think this is a bit further would be better. Say all the way across there. Rotate this all the way across, and then same thing across. Yeah, same thing across here now, and just draw a 3D shape like this. I'll draw this a bit better. Something like this. And then from the inside, this is going to be looking something like this. Draw this in 3D. This is a pretty steep shape. I'll just try to fix this, see how it looks like. And then in 3D, it will look something like this. And draw it all the way across there. And here I quickly just change the shape up just to make it a bit easier to see. And now again we have a 3D shape. Draw this dashed line across to this point. And then the surface area as well, just this shaded area around of this one segment across there. And now we'll call this shaded area, well, the surface area SI of the one segment. And now the next thing we'll do is, well, we're going to try to find out the circumference of this circle or this shape. But since this is a direct straight line, what we could do is look at the halfway point across here. Draw this in green all the way across. At this point, I'll call this at yi. Yeah, yi, and I'll put a line above indicating that it is the center of it. And then all the way across here, we're going to have a point at this point right here. And I'll call this xi center line. And the reason we're going to look at that is because we'll look at this total halfway distance, and we'll call this, well, this is going to be our ri, or the radius at this halfway of the segment, or the average radius. The same thing as writing r average. And this equals to, well, yi, so, like that with the line above. And this is the average, so this is going to be, well, yi minus 1 plus yi divided by 2, because it's a straight line segment. So we have this value across like that. And since we're rotating this around, we're going to have a perfect circle, assume it's a perfect circle. So then the circumference all the way across this whole thing is, well, from the midpoint like that, is going to be, that's going to be, I'll move this up, Yeah, that's going to be CI equals to, well, just recall our equation of a circumference of a circle, 2 pi r the radius, 2 pi r I, like that. Yeah, so now that's the circumference, and then what we'll do is just multiply by the total distance here. So what that means is, well, first of all, let's recall Pythagorean Theorem, yeah, just fix that up there, Pythagorean Theorem. And then for this case we have, well, pi, that's our distance, that's our hypotenuse. So pi minus 1 to pi, this distance squared is equal to the sides squared, so delta xi squared plus delta yi squared. And if we square root this, both sides would end up having is like this, and this is plus or minus. But since we're dealing with only a positive distance, and that's why we have this absolute value sign, the only thing that makes sense is a positive sign here for the distance. So now that we have that distance, that's going to be like our width of this this segment or this shape, and then multiplied by the circumference, and then what we get is the surface area. Remember, area is just height times width. For a rectangle, in this case, we have, well, the circumference times it by the length across, or the thickness. That's going to be pi minus 1 times pi minus 1 pi, that's just a distance. So what we have is SI, the surface area of this segment, is going to be 2 pi Ri times it by pi minus 1 pi, like that. Distance across, that's the radius. And now what we have, I'm going to remove this dot just because it make it not appear as the same as this I dot there. And now this, what this all equals to is 2 pi Ri, and then this equals to this, well, with this Ri, that is over here, that's yi minus 1 plus yi over 2. That's just the average, but this also, what this equals to is we could write this in terms of t, because this means that this is some value inside here. So then this is what this means is, because remember, this is a function of t. That's again, x is just a function of t in parametric form, f of t. So what we could do is write it as, and then that t value is in between, it's in between ti minus 1, and this is at ti. So then this is going to be equal to, well, f of ti, and I'm going to write this ti star. So this is a t or parameter value within, so within the interval of ti minus 1 and ti. Yeah, and it could be anywhere in there. It doesn't have to be the center line, because this one is center line for the x and y, but the t variable, it could be whatever. It could be as long as it's in between these. So then this is equal to, over here, that is going to be, well, this is y. And remember, y is a function of t as well, but that's g. So g of t, so then that's going to be, well, g of t I star, like that. Where that's the same one over here, within that. So we could write this as 2 pi, and now we have g ti star, and then we have it as square root, and then we plug in this part over here. So delta xi star plus delta yi star. And now the next step is, well, just the same exactly as in my earlier video on arc length. I showed that this delta xi and delta yi, we could write these, we'll rewrite in a different way by, well, recalling the mean value theorem. So recall mean value theorem, I'll just do this here all in one go. Mean value theorem, I'll put the link below in the description for the mean value theorem if you haven't already done so, check it out. So what we have is, if we look at this xi and this delta yi, what we have here, yeah, is a graph like this, and I'll do this from t, and this one, this is going to be x or y. So this will be, I'll graph two different functions at once. So for x, let's say we have something that looks like this, and let's say from here, actually I'll just change up the graph like this, and I'll call this our x graph. And now from this point, and I'll say this is from ti minus 1, this is all the way to ti. And now this distance across, that's just going to be, well, our delta t, because it's all the same distance. And then basically by the mean value theorem, it states that if we have a graph like this, basically from this point to here, if we were to draw the average slope, which is just a line from here to here, and then what we end up having is a triangle that looks like this, and then this distance across here, that's just going to be our delta xi, because that's the difference from here. This is at our xi minus 1, and all the way across here is xi, like that. So this total distance is like that, and this is delta t. So what that means is there has to be a point like this somewhere across here where this slope is the exact same as this line across there. So I'll just draw this further across. So this is parallel to this line, and what that means is that there's a point all the way down here at ti, and I'll call this double star because we already have a star. Yeah, let's put the double star again. So now we have a ti double star where the slopes are the exact same. So at this point here, by the mean value theorem, this slope is, well, this could be written as, because this is for the x function, f prime of now ti star. So ti star like this. This equals to, has to equal to just the rise of a run, or the average slope. In other words, delta xi over delta t. And now we could do the exact same thing for the y curve, and I'll just draw this in red. Let's say from here to here we had something that looks like this, etc. So from here to here, actually I just fixed it up just to make it easier to notice. Let's say this is our y curve, and then again from here to here this is the average slope across there, and then at this point here is yi minus 1, all the way at the bottom there is yi, like that, and that's all the way across here. So now this distance across is our delta yi, like that, and then again there's the same distance at the bottom, just a right angle triangle. So then there has to be a point somewhere in between. Let's say it's somewhere over here, like this, and then this point all the way across here, and I'll put this one as ti triple star, so another random point. So again, by the mean value theorem, we have now g prime, or the derivative at this triple star like that. Yeah, this triple star like that is equal to, and before I get to that, I gotta add another star there. Let's put another star like that, just because I made a mistake. So I just fixed it up and fixed the color. So now this means now we have delta yi like that over delta t. And in this particular case, this will be negative, etc., because we're going down to negative slope. But basically, so the exact same thing here. So what this means is we can move this over to the other side as well as this, and then throw this inside, so then we have delta t and then f prime ti double star, and then throw this inside there, and then this goes over there. So we have everything in terms of ti, even though there's ti star, ti double star, and ti triple star, etc. So what we end up having is, well, si, and I'll just throw this down here, a better arrow like this, all the way across to here. Si is equal to 2 pi g, and now we have ti star, just to see if we have it correctly. So we have ti star, and then square root, and then we plug in this f prime ti double star, and then move the delta t on this side. So we end up having is like this. This equals then we have a square root. So now inside this we are squaring, instead of delta ti, we put this f prime double star, and then times it by delta t. So now we have it as f prime of ti double star squared, and then as well as delta t squared like that, and move this square root even further, plus now the same thing for the g. So g ti triple star squared, now delta t like that squared. And now finally what we could do, now we could simplify this further, and I'm gonna write this. Actually, not right. I'm just gonna move this delta t. We're gonna factor out this delta t squared because it's a multiplication on both sides. We could factor out and then take the square root of it, so then we cancel the square. All we get is a delta t. So what we get now, and then also take the limit as n goes to infinity. So what we end up having is S, the total surface area, is equal to the limit as n approaches infinity, because now that was just one segment, now we sum up to infinite number of segments, as I is equal to 1 up to n. Just fix that summation. So we take the limit as n approaches infinity of the summation, or I is 1 up to n of Si, which is each segment, so we sum it up and then also do this all in one go. So now this equals to limit as n approaches infinity of now the summation I equals 1 up to n, and then just plug this inside. So 2 pi g ti star, and then we do the square root like this, square root, and then just plug this in. So now we have f prime ti double star squared plus now this part g prime ti triple star squared, and then the delta t, we factored that out, delta t squared, and then we square root it, so we just get delta t on the outside like this, like that. So there is what we have. It looks like a Riemann sum. So yeah, like before, when I did the part 3 video on arc length for parametric curves, I also pointed out that note that since in general ti star does not necessarily equal to ti double star or ti triple star, so none of these have to equal each other, as you can see, but they're all between this delta t. So there's ti double star could be somewhere there, this ti triple star could be somewhere there, and likewise the ti star could be anywhere else, because that just corresponds to the average x and y points, and it could be somewhere anywhere like this. For example, this could be the ti star. I'll put a question mark because we don't know where it is, etc. So it could be somewhere there, but it's all between these delta t's. So again, so this summation is not exactly a Riemann sum because they are not necessarily equal. And recall my earlier videos on Riemann sums, that's when those are all equal. And but note that, fix that typo. So note that as n, the number of segments, approaches infinity, then our delta t approaches infinitely small value. In other words, it's approaching 0. So in order for this to get infinite number of segments, we basically have to get increasingly small number of the distance of the intervals of the delta t. This means that ti star, ti double star, and ti triple star all approach the same value. Let's just call it t, since they are all within the interval ti minus 1 to ti. So if we're taking this to infinity, the number of segments, then this is just getting smaller and smaller. And again, these are all within this, so then basically these all approach the same value t, so some random point there, and we're just dealing with infinitely small values. So thus, as n approaches infinity, the summation does in fact approach the exact definition of a Riemann sum. Thus we can write it as an integral. So what we end up having is, well, s is equal to, by definition of the Riemann sum, since we're approaching it, s is equal to the surface area integral from alpha to beta of 2 pi. Now we just use it as the value. These all approach the value t, just a random point t, and then square root. So write g of t like that. Square root now f prime of t squared plus g prime of t squared, and then we have a dt. So the delta t approaches infinitely small. Call that dt, like that. That's just our delta t approaches dt, infinitely small distance across. And now if we write in Leibniz notation, this equals to what we're more accustomed to, integral from alpha to beta of 2 pi, and then this is just y, g of t is just our y, and now we have this is the dx, the derivative over t, so dx over dt, plus now this part is dy over dt squared, and then we have a dt like that. Yeah, and there is our formula like that, and this is in fact the exact same as what we were trying to prove. And well, this one is for when y equals f of x. We have this integral from alpha to beta of 2 pi y, then square root dx over dt squared, and then plus dy over dt squared dt. And again, let's put a big check mark here. This is the exact same. So there is our proof and by using polygonal approximation and using mean value theorem, and also rationalizing how it's the same as a Riemann sum, or approaching it. So anyway, that's all for today. Hope you learned from this very extensive proof video, and hopefully you followed it along slowly. It's pretty interesting, so just keep that all in mind. This is why I like doing these videos, because it shows you just the amount of meticulous and tedious work behind a lot of theorems like this. It's used in a lot of applications in physics, engineering, even your laser printer is probably using this to calculate the surface area to see how much ink it uses, etc. Anyways, that's all for today. If you learn, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another math easy solution.